next session of our conference. So our first speaker is Karoly from Budapest University of Technology and Economics, and he's going to tell us about dimension estimates for C1 iterated function systems. Please.
Thank you. So first of all, I would like to join to other participants in greeting Felix on the occasion of his 70th birthday. I visited Felix for the first time 30 years ago for a month, and it was a very, very useful visit for me because I had a paper in that time about the computation of some attractors with transversality method. Which transversality method will play an important role in this talk also. And Felix gave me an advice how to shrink the presentation of the proof to 1/3 of its original length. So it was very influential and very, very useful. And since that time, I have visited Warsaw several times, working together with also Michal Ramsalot. Mostly we work with Michal, but also we learned a lot from Felix. So what I would like to talk about it is dimension estimates for C1 iterated function systems. And whatever I speak about, all the new results are joined with Daejun Feng from Hong Kong. Now, what I would like to tell you it is that we have two papers on this subject, two joint papers. And 2 years ago, I gave a talk at Bedlevo also, and later at Warwick about the first of these two papers, which were the upper estimates. And then we will give lower estimates in this talk for the attractors of C1 iterated function systems. So what is the C1? We are going to consider iterated function system C1 iterated on RD. I cannot draw in RD, but it's very much essential that we are not on the line, but in higher dimension, just because I can draw better on the line. Therefore, you can think of something like this, but in higher dimension. So there is a set, which is a compact set in RD, such that there is an open set which contains this previously mentioned compact set Z, with the following property that each of the mappings, as you see on the picture, since this Z is noted over here, I hope that you can see this interval is Z on the picture, and U is an interval which is slightly bigger than Z, and then each of these mappings sends U into itself, and Fi is a Z1 function of this open sets U, and each of these mappings are contractions, and the common they are uniform. I mean that their Lipschitz constant are smaller than 1. We consider the attractor. The attractor is the unique non-empty compact set which satisfies this kind of self-similarity equation. But I think it's better if I show it to you over here. So you can imagine that this is Z, which is a compact set in RD, and all of these maps, as we assumed, send Z into itself, as you can see over here on this picture. So these sets F1Z, F2Z, FLZ, because we assume that there are little l, whenever I write little l, it stands for the number of the mappings in this iterated function system. So we have little l mappings, and each of the images are contained. So that's why the union, what is striped over here, is a subset of Z, and this implies that if you take the n-fold iterations, whenever I write Fin, it always means Fi1 composition Fin. So this is simply an arbitrary n-fold composition, and in N, this red union forms a nested sequence of sets. It's getting smaller and smaller, and if you take the intersection, then you get the attractor, which is one more time the unique non-empty compact set satisfying this equation. And our goal is to get a better understanding of this. Yesterday, Sasha Torchai gave a talk about the Selfrefine case, which somehow included a little bit also something about self-similar situation. It's already very difficult. I mean, the Selfrefine, but when you consider mappings which are neither affine nor conformal, then the situation gets much more difficult. Even the upper bound for the dimension of the attractor was difficult, and we can give lower bound only in some special cases, and this talk is going to be about those special situations. I use two kind of screens. One of them is bigger, but on the other one I can write, and that's why I switch sometimes. So some notation, the symbolic space, whenever we talk about an iterative function system, we need a symbolic space. As I mentioned, I just like to recall that we have L functions. So our, I'm sorry, I need to do this, L functions. So this means, just to recall that this iterative function system is like F1, FL, and that's why this is the symbolic space, which is sigma, and a cylinder in the symbolic space omega 1, omega n. It is just the set of all infinite sequences such that the first n digits coincide with the digits of omega. And whenever we speak about an iterative function system, we always need a coding map. I'm sorry, this is somehow too, just a moment. And I go back, it will be okay. Good, hopefully. So this is the coding map, which gives you the codes of the elements of the attractor, the codes of the elements of the attractor in terms of the elements of the symbolic space. Now, we would like to somehow using some tools to estimate the dimension, and to estimate the dimension, the host of dimension, box dimension, and also the dimension of the push forward of the ergodic measures. For that, we need some notation. First, we introduce what is the subadditive potential. In general, the subadditive potential is something like this. So it is a sequence of continuous functions on the symbolic space. Just like to recall that sigma means the symbolic space. Maybe better if we just go back to here and here. Just a moment. So sigma was the symbolic space, and these Gn functions are just continuous functions on the symbolic space, and they are subadditive. So they satisfy this property Gmni is more than equal to Gni plus Gm sigma I. I just write it down because it will be very important later. So this is more than equal to Gni plus Gm sigma Ni, where I is just an arbitrary element of the symbolic space. So this means subadditive potential. So for a subadditive potential, we define the topological pressure, and the topological pressure for the subadditive potential. I believe that everybody in this audience knows about the usual topological pressure. Now this is something similar the topological pressure of the subadditive potential is defined in this way. Maybe I just go back to have a bigger picture. So what you see here at the beginning, this it is just to express that we will take the exponential growth rate of something, and here you add up for all n cylinders. So these n cylinders will, one more time, just elements of this space. So these omegas, this was sigma n. So these omegas were chosen from here. And then what we do it is that we simply take this gn, and actually the exponential of gn, what we want it is that we take the supremum on each of these cylinders. So this is just the supremum, and this will be the pressure by definition. Now, if you want to compare it to the usual pressure, then what you can see it is that in the case of the usual pressure, this Gn is just a continuous function. G is evaluated on the first n element of the orbit. So in this case, if you substitute here for Gn, you substitute the sum, then you get back the usual pressure, what we are used to. Yes. So this was the pressure, and it will play a very, sorry, it was over here, and it will play a very important role, because using the pressure, we will be able to express our best guess for the dimension of the attractor. Now, another important thing what we needed is the Lyapunov exponent for the subadditive potential. One more time, the subadditive potential was Gn. With Gn satisfy this subadditive inequality, and then the Lyapunov exponent for the subadditive potential is defined by this limit, and because of the subadditivity, this limit exists and is equal to the infimum. It doesn't say much, but we will consider this Lyapunov exponent for a specific potential Gn, which I will specify a little later. But all until now, we have defined two things. One of them was the Lyapunov exponent, which is this limit of 1 over n times the integral, and the other one was the pressure, which pressure was just a little bit different from the usual pressure. You all know the usual pressure, and instead of what you have in this bracket, there we wrote the nth element of the subadditive potential. This was the subadditive pressure introduced by Falconer in 1993. The variational principle was proved by Chao, Feng, and Huang in 2008, which says that the pressure is the supremum of the entropy plus this Lyapunov exponent. The Lyapunov exponent was defined over here. So this was the Lyapunov exponent, the entropy plus Lyapunov exponent, and the supremum is taken for the invariant measures. Actually, Feng proved a little later that there exists at least one ergodic equilibrium measure, so the supremum is attained for at least one ergodic measures, even in this situation when the pressure is the non-additive pressure, and this is the Lyapunov exponent for that. Now, I would like to explain you what will be the reason for the specific choice of this Gn, because this Gn will carry the information about what price we need to pay to cover the attractor, basically. So this is the next slide, what I'm going to do. The idea is, this idea came from Falconer, and all of this notation comes from the theory of self-affine iterated function systems. So the first thing is that we imagine that somehow this is big now. So that this what you see over here, this green box, this is basically an end cylinder for a Selfrefine attractor. And the idea is somehow that when what we are doing now, it is that we try to find out what is the most natural cover in the Selfrefine case when you consider the Selfrefine iterated function system. So if this is an end cylinder, then the size of the end cylinder somehow connected to the these alphas are the singular values of the mapping. So here is this bi is that there is some linear part of this Selfrefine mappings, and bi is this aix, ai times x, where x is an element of the cube. And then if alphas are the singular values of this is an n-fold composition of n-fold matrix product, and alphas are the singular values, then you can see that there are three natural ways to cover this rectangular box. Either you cover it with the biggest side, which is alpha 1, what you see over here. So you cover it with the biggest side, and then what is the host of dimension? Somehow this whole thing is a little too big. Just a moment. Okay, I need to shrink the size. So the definition of the host of dimension is here. When you want to compute the host of dimension, then basically you can study this orange sum. And the idea is that we cover all the level and cylinders individually, and we want to compute that if we do that, and we cover in the most natural way, what is the contribution of such a level and cylinder to this sum. And if we cover with a box which corresponds to this biggest singular value, then for this sum, the contribution is alpha 1t. And if you choose the second singular value as the size of the boxes with which you cover, then you need how many boxes you need. This is the number. Here you see the number of how many boxes you need, and then each individual box of side alpha 2 has this contribution. So altogether, this is the number what you contribute. And if you choose to cover with the smallest side, then altogether the number of the many cubes you see there is alpha 1 divided by alpha 3 and alpha 2 divided by alpha 3. This is the number of all the cubes that you see, and each individual cubes contribute with this amount. So you get in the first situation this, in the second, and in the third situation. Now the question is, because we would like to choose the smallest one, which one is the smallest? And it turns out that among these three, which is the smallest, the answer is that it depends on t. Actually, the smallest one, you get the smallest one for t integer value. So integer value t gives you the smallest one. If t is smaller than 1, then this is the smallest. If t is between 1 and 2, then this between 2 and 3, then this is going to be the smallest. And that is the reason that we define the singular, it was defined by Falconer, the singular value function, because the smallest among these and this and that is the one when you choose, well, this number, which is -0, -1, -2, you just need to subtract the integer value of t, it gives you the smallest price of covering, the smallest price, meaning that we cover one more time all the exponentially many cylinders individually, and we have seen three possible ways to cover it, and then the contribution to the sum, which defines the host of dimension, can be expressed. This is basically the price of covering such an cylinder in the most natural, in the most primitive way. That's why this plays a very important, this is called singular value function. Now here there is a typo. This is supposed to be normal phi. So whatever you see over here, these are not, these are just normal phi. This phi t is a singular value function, and it is sub-multiplicative. So if you take logarithm, it will be sub-additive. And that's why this is a very important point, because here we can define this subadditive potential we work with. And you see the reason for that, because this plays the role of the matrix which is over here, and this is just the singular value function. I mentioned that we define the pressure in this particular way. This was the definition of the pressure. But if you substitute this Gn over here, then this logarithm eats up the exponents. And what you see over here, this is the pressure, and we consider it as a function of S. So one more time, this is just the exponential growth rate of the sum. In the sum, you have exponential many summands, and each of these summands somehow expresses the price of covering, the price in this sense, the price of covering one of the exponentially many cylinders. So this was that's why this pressure is related to the dimension. Now the function PS is continuous and strictly increasing. It has a unique zero, and this unique zero is the singularity dimension of F. Now, this will be basically the expected value of the host of dimension. This should be the host of dimension. If everything works well, then the root of PS should be the dimension. Why the root of PS? Because basically, so this is basically PS. So this is the function S to PS, and if you choose, I'm sorry, and if you choose an S, so this is the root, which we call the singularity dimension of this iterated function system. But if you choose T prime, which is smaller, then this PS is going to be positive. And if PS is positive, it means that the exponential growth rate of the sum is positive. It means that it tends to infinity. And if you choose T tilde, which is bigger than this singularity dimension, then the exponential growth rate of the sum will be zero. It means that this covering sum will tends to zero. So if you remember of the definition of the host of measure, somehow it suggests that this should be the dimension. The reason that we don't know that this is the dimension is that we do not know if this cover we just described above is the most effective cover. It is the most natural one, but we don't know if it is the most the most effective one. The next thing I like to discuss, it is the Lyapunov exponent. In our case, the Lyapunov exponent is a little bit different. So the Lyapunov, we consider the ice Lyapunov exponent of the, so let M be a measure, an ergodic measure of the symbolic space. And for this, and alpha I, it is alpha I in general is the i's biggest singular value. So in this case, A is this matrix what you see over here, and for this matrix we take the i's biggest singular value, and we take its logarithm, and then we define the i's Lyapunov the i's Lyapunov exponent. Now, using this i's Lyapunov exponent, if you recall, this was the definition originally. So this was the original definition of the Lyapunov exponent of GS. Sorry, here I should have written S because this GN, as I mentioned, this depends on S. The dependence on S is very important. So when we write here S, then here we should write S. And this is not the S power, just the index, super index. Now, based on this definition, based on this, you can write down from this definition using this expression, we can write down that the Lyapunov exponent of this subadditive potential can be expressed by this formula, which is not an inviting formula. So I just drew the graph of this function, which looks much better, believe me. So this formula, which you see over there, maybe I go to just Control L. No, it gives too much for some reason. So this formula, that we have here gives you the following function. What you see here, this is the negative of the function actually, that in between 0 and 1, you move with the slope negative lambda 1m. Maybe it's better now if we come here. So here between 0 and 1, the slope of this segment is negative lambda 1, and between 1 and 2, the slope is negative lambda 2, and so on. And in this case, d is equal to 3. So after 3, the slope is just, as you see, lambda 1 plus lambda 2 plus lambda 3 divided by 3, actually the negative of that. So this function, what you see over there, it is this blue line function over here. And then how do we define the Lyapunov exponent, the Lyapunov dimension of a measure? The Lyapunov dimension as a measure is the value, if you take the value at this point of this negative GSM function, if you take at this point, then you get back the entropy. So basically, how do you get this value? You just take the entropy over here and you move in a horizontal way until you meet the graph and you drop down. And this is the Lyapunov dimension of the measure. And this is the best guess for the dimension. It doesn't look very much inviting, but I can explain why it is natural. Imagine that all of the Lyapunov exponent of the measure, all of them are the same. So we are, for example, if we are in the conformal case, then all of the Lyapunov exponents are the same. And if they are all the same, then what you see here, then there is actually one Lyapunov exponent. And then what you get here by this definition, because in that case, this blue line function is just a straight line. And what you get as a dimension here, this Lyapunov dimension, is just entropy divided by Lyapunov exponent, entropy divided by this Lyapunov exponent, which all of you have heard as a good candidate for an ergodic measure. So this is just a generalization. This notion of Lyapunov dimension is just generalization of the formula entropy divided by Lyapunov exponent. Yes. And then I just like to mention what is the relation between the Lyapunov exponent and the Lyapunov dimension. The singularity dimension was defined as the root of the pressure formula. Earlier, I said that you imagine the pressure function like this. This is S2 PS, and this is the singularity dimension of the system. And the singularity dimension is just the supremum of the Lyapunov dimension for the measures, and the supremum is attained by at least one ergodic measure. And this is an obvious formula. L was the number of functions, and theta is the common Lipschitz constant for the system. Now we have all the important notation. And what I like to tell you that 2 years ago, when I was at Bedlevo and Warwick, I gave a talk about our previous result with Dai Jun-Feng, in which we proved that the singularity dimension and Lyapunov dimension are indeed upper bounds for the dimension, the appropriate dimension of the attractor, so the upper box counting dimension and the packing dimension of the measure. Packing dimension of the measure is bigger than equal to Hausdorff dimension of the measure also. And we prove it for all C1 IFS. We proved it. This was the upper bound, and there were not too much restrictions, just it was a general formula. Now, the new results, by the way, when am I supposed to finish? Could you tell me, Leticia?
Yeah, so you started 10 minutes late. So I think you have until 12:10.
12:10.
So 15 minutes, 15 minutes, yeah.
Okay, thank you. Good, good. So I can state the theorem. We need two conditions. One of them is what a dominated lower triangular iterated function system. So we consider, sorry, a C1 IFS on RT. And we say that this is dominated lower triangular if all the derivatives are lower triangular matrices, and in the diagonal, the values are in decreasing order. But when you take the absolute values, then in decreasing order, on the upper left corner, you have the biggest one, and then it goes down for you in this way. It just goes down. This is the dominated, is dominated because of this, and lower triangular because it's lower triangular. So this will be one of the conditions we use. And then there will be another notion we use. It is the direct product of IFS. I don't want to give you the general definition. You can take a direct product of any finite number of iterated function systems. I just like to show it to you in the case when there are two iterated function systems. So the red iterated function system, which sends this interval into these two intervals, as you see, this is the red iterated function system, and it is drawn on the x-axis. And there is a blue iterated function system which comes on the y-axis. And the product of the red and the blue iterated function system is this one. So the product doesn't have 4 mappings. It has only 2 mappings, because we can take the product if the number of mappings of the red and the number of mappings of the blue are identical. And the first coordinate is determined by the first iterated function system, and the second coordinate determined by the second one. So this is the meaning of the product of iterated function systems. So there was the dominated lower triangular. Dominated means that so it's lower triangular, and in the diagonal from up to down, the values are in decreasing order. And this is the direct product. Now, translation family. Actually, you need a third notion, which is the translation family. So we cannot hope to have lower bound in all cases. We do not have lower bound even in the self-similar case. So we can hope when we give the lower bound only to give some almost sure result. So it's natural to consider one particular C1 iterated function system on a compact set Z. And then we take its translates. So each of the functions individually are translated with a vector. This iterated function system is in RD, so each of these Ti are in RD either. So this tuple of d-dimensional vectors, this very angry T, is in the L times d-dimensional space. And we choose this translation so small that this relation must hold for every Ti. So it's just a small translation. And we would like to prove results for typical Lebesgue typical small translation. So this is the translation family, starting with an IFS individually, independently, we translate the elements with a small amount. This is the translation family. And just for notation, D means dimension. So this D is not related to the dimension of the space, but just we would like to express that this is the dimension. And if you write dt, it simply means the singularity dimension. So one more time, the singularity dimension was, the singularity dimension was the root of the pressure formula. So this was this pressure, and this is the singularity dimension. So this was the root of this, and the d mu t is basically the extension to the non-conformal case. We extend the entropy divided by Lyapunov exponent. So this you have heard about. A good guess for the dimension in the conformal case is entropy divided by Lyapunov exponent. And if we are not in the conformal case, then we need to do something more complicated. But this Lyapunov dimension is the extension of that. And we write just d mu t for it. Good. And now with these notations, in order to state the theorem, I need some conditions. So the theorem has conditions and conclusions. Now I state the conditions of the theorem. We have a C1 iterated function system in RD. And one of the three things should happen. Either F is a dominated lower triangular. With this assumption is necessary. This is necessary even in dimension 1. This assumption somehow helps us to use a certain kind of transversal condition. Without that, we don't know how to it simply means that if all the contraction ratios are smaller than 1/2, then certainly this assumption holds. But it can happen that one function has a very big contraction ratio, I mean Lipschitz constant, very big. I mean very big means that close to 1, but all the other functions have very tiny. So whenever you take the Lipschitz constant of any two functions, they add up to something less than 1. This is an important one. So either it is dominated lower triangular or C1 and conformal, or any kind of product of these two. And then our result says that if you take this translational family that I mentioned above for such an iterated function system, which satisfies one of the conditions, maybe it's better to go to the place where I can show you both of the Okay, it's here. So here are the conditions you see, and if the iterated function system satisfies, if the iterated function system satisfies one of these conditions, then the dimension of the attractor or any push-forward ergodic measure can be computed by the singularity dimension for the attractor or the Lyapunov dimension for the push-forward of the measure. What does it mean exactly? Here it is written in a more precise way. So under the conditions, this one of the three condition holds, and if mu is an ergodic measure on the symbolic space, then for almost all translation, the push-forward measure is exact dimensional, and the dimension of the push-forward measure can be computed by the Lyapunov dimension. And if this Lyapunov dimension is bigger than the dimension of the space, then the push-forward of the measure is absolute continuous with the Lebesgue measure. The result for the attractor is that for almost all translations, the dimension of the attractor almost surely it can be the box or Hausdorff dimension can be computed by the singularity dimension, and if the singularity dimension is bigger than the dimension of the space, then the Lebesgue measure of the attractor is positive. Now, how do we get this result? I just like to say, because our result is a slightly little bit more complicated, it depends on parameterized families are just like families like the translational family. Translational family is one example of parameterized families, and for these parameterized families, we needed to establish a transversality condition, which transversality condition was suggested by the transversality condition that we introduced by Thomas Jordan, Mark Policott, and myself some 14 years ago, with some modifications. We needed, first of all, a function which for every finite word I, we needed such a complicated function. The definition of the function is here, but I drew the function in 2 dimensions over there, and using this function, which is complicated indeed, but using that, we can roll down something what we call generalized transversality condition. And this generalized transversality condition basically says that if our parameter, the eta is just a reference measure on the parameter space, it is usually the Lebesgue measure on the parameter space. And if this condition holds, we say the general transversality condition holds, this is the condition itself, basically. So it says that there exists a delta 0 and the function psi delta, which tends to 0 at 0, in such a way that we can choose a constant C, such that for every ij, which are distinct elements of the symbolic space, this yellow inequality holds. What is this yellow inequality? I like to explain it in a minute. This is usually the Lebesgue measure. So the Lebesgue measure of those parameters for which the distance of the push forward of I and j are close to each other. This Lebesgue measure, when they get close to each other, is smaller than something. Now, what is this? In the usual transversality condition, here should be simply R. But you see, this is almost R. We just need to take into consideration some other parts, which is to reflect that we have more than one Lyapunov exponent. So this function, what you see over there, appears here, and what did not appear in the usual transversality condition, it is this factor, which is ij. This is the joint part of ij multiplied by psi delta. I just like to remind that psi delta tends to 0. So basically, this condition is about that you choose a T0 and a small neighborhood of T0, and this neighborhood will appear over here, because by this vector, you see this is bigger than 1, and by this vector, we lose something from the dimension. Basically, we use psi delta for the dimension, but we let delta tends to 0, and what we lose from the dimension, it somehow disappears for that. So under this condition, if you have this generalized transcendental condition, then all kind of assertions hold typically under this. And I have 2 minutes left for history. Usually people start with history, but I want to finish with history for some reasons. So the very first paper in this direction was due to Falconer in 1994. He gave upper bound for the dimension, not in C1, but in C2 case, and he used a property, which is a one-bunch property, which is a technical property, which says that if one direction a contraction is 1/3, then no other direction can the contraction be stronger than 1/9. Something like this is the one-bunch property. And then under that, he gave upper bound in the C2 case. Barreira published related results, similar flavor, just more general in 1996, and Hugh extended the scope of Falconer theorem. And then Zhang made a very important achievement. He extended Falconer's theorem, what I mentioned over there, for C1, and he proved it without one bunch, but he can prove only the upper estimate for Hausdorff dimension. And with Mariusz Urbanski's, Boris Solomiak, and myself, we obtained similar results for C1 plus epsilon conformal iterated function system, results which are similar to what I mentioned in this talk. And Barreira gave an upper bound, but unfortunately it was incorrect. And with Jordan, Thomas Jordan and Mark Policott and myself, we established a transversal condition for the self-similar case, so that our general transversal condition I mentioned here is a generalization of that. And I just like to mention Bonchow, who proved an equivalence of seemingly different definition of this subadditive pressure, and a variational principle was proved for subadditive pressure by Chow, Feng, and Huang, and thus Shimon's constructed self-affine sponge, whose dynamical dimension, that is the supremum of Hausdorff dimension of the invariant measure, is strictly less than its Hausdorff dimension. Thank you very much for your attention. I finished.
Thank you.
Thank you very much from that level.
So are there any questions from that level in the room?
No, I can't see any questions.
Right. And what about the online participants? Any questions? Okay, so everything was very clear. Well, let's thank the speaker again for the nice talk. And maybe we are a bit behind schedule, but we